In December 2022, something happened that sounds like science fiction, except it was measured in megajoules. At the U.S. National Ignition Facility, scientists fired lasers into a tiny fuel pellet and triggered a fusion reaction that released more energy than the laser energy delivered to the target. Then they did it again and again. By 2025, reported yields climbed dramatically, proof that ignition wasn't just a one-off headline. It was repeatable physics. So why aren't we building fusion power plants everywhere? Because the most powerful energy breakthrough in modern history ran into a villain nobody put on the poster, the rule book. Here's the paradox that makes this story feel like a thriller. Fusion isn't explicitly illegal. No country has a fusion ban law. But in key places, it's stuck in a kind of bureaucratic force field. Legal to invent, nearly impossible to license at commercial speed. In the U.S., a lot of nuclear licensing still traces back to frameworks designed around 1950s fission risks, meltdown scenarios, long-lived waste, and proliferation assumptions that don't map neatly onto fusion's physics. Fusion can still involve radioactive materials like tritium, and components can become activated by neutrons. So yes, it needs oversight. But treating fusion like fission is like regulating drones under airline rules, because both have wings. Meanwhile, private fusion companies are pouring billions into machines with real timelines, some even signing power delivery deals. China is sprinting. Investors are watching the calendar, and the energy transition clock is ticking. So the question isn't can we do fusion? It's who gets a turret on first, and who gets trapped waiting for permission. Fusion is the ultimate clean energy promise. No carbon emissions during operation, no runaway chain reaction like fission, and fuel sources that are, in principle, staggeringly abundant. And yet, the moment fusion stopped being a theory and started looking like an industry, it hit a weird wall. We don't have a modern lane for it. In the U.S., the Nuclear Regulatory Commission is one of the most serious safety institutions on Earth. That's not the problem. The problem is that the main licensing DNA for nuclear was written for a different beast. Fission reactors, machines where safety is defined by controlling a chain reaction and managing long-lived waste. Fusion has different hazards: tritium handling, neutron activation of materials, radiation shielding, worker exposure, and robust containment systems. Real risks, yes, but not meltdown risks in the classic sense. So fusion companies get stuck in a catch-22. If they move fast, they run into a licensing process that can take many years and cost enormous amounts. If they wait for a fusion-specific framework, they risk burning investor time and momentum that, if they build anyway, they can end up with a reactor that exists but can't legally connect to the grid or operate commercially at scale. That's why people say they got banned. It's not a courtroom ban. It's something more frustrating, a timeline mismatch. Venture-backed companies move in 2 to 5 year horizons. Nuclear-style licensing can move in 10 to 15, and then the geopolitical pressure kicks in. Because regulation isn't happening in a vacuum. China is funding fusion as strategic infrastructure. The U.S. fusion breakthrough happened inside a national security context. Europe has ITER, an international marvel and a cautionary tale about how multi-country governance can stretch timelines into decades. So here's the tension that makes this story bigger than energy. If fusion becomes real in the 2030s, the winners won't just sell electricity. They'll export the standard, the supply chain, the talent, the geopolitical leverage. And the scariest possibility is this. What if the country that proved fusion works is the last country allowed to deploy it? Next, we need to talk about the proof itself, what ignition did, what it didn't do, and why the headline is both true and dangerously misunderstood. When people heard net energy gain, a lot of brains auto-translated it to, okay, so fusion power plants are basically ready. That's not what happened. What happened is subtler and more historic. At the National Ignition Facility, NIF, the experiment crossed a line fusion scientists have chased for decades. Ignition, where the fusion reaction becomes self-heating enough that the output from the fuel exceeds the energy delivered to the fuel capsule. That is an extraordinary physics milestone, but it also created the biggest misunderstanding in fusion. NIF's net gain is measured against laser energy delivered to the target. not the total electricity drawn from the wall plug to power the lasers and facility. In other words, it's a proof of scientific feasibility, not a blueprint for a power plant. So why does it matter so much? Because fusion progress has always been haunted by one question. Are we chasing a mirage, or is there a real threshold? Ignition answered that, loudly. It told every engineer, investor, and startup founder, the mountain has a summit. We now know the laws of physics allow a controlled fusion burn that produces more energy than it receives at the fuel level. And the private sector reacted like a starting pistol went off. Over 40 companies are now pursuing different paths: tokamaks, stellarators, magnetized target fusion, laser systems, pulse approaches, advanced fuels. Some are building demonstration hardware right now, with public timelines aimed at late 2020's milestones and 2030's commercialization. Here's the key emotional beat. For decades, fusion was always 30 years away, because nobody could prove the hardest part. Now, the hardest part is partially proven, so the bottleneck shifts from physics to engineering, and then to something even less glamorous: permission. Because the moment you can plausibly build a machine that makes power, you have to answer. Who regulates it? Under what rules? How long does it take? What counts as safe enough? And the next twist is brutal. Even the countries trying to be pro-fusion can accidentally sabotage it, sometimes overnight. Let's do the simplest physics to policy, translation possible. A fission reactor is like a pile of hot coals. Once it's going, safety is about preventing the heat from running away. A fusion reactor is more like a candle flame in a hurricane. It only stays lit if you hold the exact conditions: temperature, density, confinement, perfectly, lose control, and the reaction stops. No chain reaction. No keep-going momentum. The plasma cools and the show ends. That's why international safety summaries often emphasize a core point. A runaway fusion chain reaction is physically impossible. If conditions drift, fusion shuts off. But can't melt down doesn't mean no risk. Fusion still has real engineering hazards. Tritium, radioactive hydrogen used in many fusion fuel cycles. It needs careful containment and accounting. Neutron activation. High-energy neutrons can make reactor materials radioactive over time, creating waste that must be managed, typically shorter-lived than fission waste, but still regulated waste. Radiation shielding and worker safety. Serious industrial safety engineering, not a casual lab toy. High-powered magnets and high-voltage systems. For some designs, mechanical and electrical. Hazards at extreme scale. So here's the regulatory mismatch. Traditional nuclear frameworks were built around long-lived, high-volume radioactive waste criticality, and chain reaction, control meltdown scenarios, fission-specific emergency planning assumptions, proliferation pathways tied to fissile materials. Fusion doesn't neatly fit those boxes, but if you force it into them, you get requirements that are either irrelevant or massively overbuilt, like demanding a gasoline engine emissions test for an electric car because both use roads. That's why fusion companies argue for risk-informed regulation, rules that match fusion's actual hazards, not a hand-me-down fission template. And this isn't just abstract bureaucracy. It shapes everything. How quickly you can test prototypes, how much capital you need before revenue is even possible, whether investors believe your timeline, whether talent stays, or leaves for jurisdictions with clearer pathways. Now here's where it gets spicy. The U.S. is moving toward a fusion-specific approach, but the timeline matters. If your machine is ready in 2028 and the licensing lane opens in 2031, that's not slow. That's existential. So next, we follow the money and humans. Who's racing ahead, what the private sector is actually building, and why the first real fusion electricity might come from a deal that bypasses a grid entirely. Fusion isn't just a science project anymore. It's a countdown, because the world is entering an era where electricity demand doesn't just rise, it spikes. Data centers, AI training, electrified transport, heat pumps, industrial decarbonization, all of it turns a grid into the new battleground of prosperity. And in that context, fusion isn't competing with renewables like solar and wind. It's competing with something uglier: delay. Every year a clean baseload option is stuck in limbo. The grid leans harder on Fossil plants kept online just in case, gas peakers for reliability, overbuilt transmission, and storage that take years to permit geopolitical fuel, dependencies that keep prices and politics volatile. Now zoom into the private fusion companies. Their biggest constraint isn't plasma temperature. It's runway. Venture-backed timelines don't tolerate, maybe you'll get a license in a decade. They tolerate milestones, prototypes, and credible paths to revenue. That's why you're seeing companies do something that looks like a workaround but might become the future. Sell power, without being a traditional utility. Instead, connect to the public grid and serve everyone. The earliest fusion deployments could look like a dedicated plant powering a hyperscale data center, an industrial customer buying heat and electricity directly, a private microgrid model with fewer regulatory layers than national grid integration. If you've ever wondered why a tech company would sign an early power purchase agreement with a fusion startup, that's the logic. Lock in future baseload clean energy before everyone else has access. And here's the human angle nobody says politely. Fusion has become a talent magnet. The best plasma physicists, magnet engineers, materials scientists, and control systems experts can now choose between national labs with slow, cautious timeline startups with aggressive goals, and huge upside countries offering clearer pathways to build. Regulation doesn't just decide safety. It decides where people live, where factories get built, and who owns the supply chain when fusion stops being research and becomes industry. Which leads to the next segment, the global map. Because one country tried to become the fusion safe haven, then abruptly changed its mind. Another is sprinting with state-backed speed. And the U.S. is rewriting the rules while the clock keeps running. So who's actually positioned to flip the switch first? If you want to predict where fusion gets deployed first, don't just watch the science, watch the paperwork. The United States will build a new lane soon. The U.S. has world-leading research credibility and an exploding private sector. But fusion companies have been staring at a licensing gray zone, regulated like nuclear, but not clearly categorized like fission. The NRC signaled it would develop a fusion-specific framework, but the key detail is time. Proposed rules, final rules, implementation. The process can stretch across years. That's not inherently wrong. Good regulation takes work, but it creates a brutal gap between engineering timelines and legal readiness. And in that gap, startups do what startups always do. They route around the obstacle. The United Kingdom. Come here. We're fusion-friendly. Wait. Never mind. The UK briefly looked like the fusion entrepreneur's dream. A national strategy, public investment, and legislation that suggested fusion might be treated differently from fission and regulation. Then came the reversal. Signals that fusion would be pulled back under more traditional nuclear-style regulation. Even if the intent is safety and consistency, the market reads it as uncertainty. And investors hate uncertainty more than difficulty, because difficulty can be priced. Uncertainty can't. China, build first, standardize later. China's fusion pushes state-backed, strategic, and fast. Projects move with the logic of national infrastructure. Build capacity, iterate, learn, scale. That can create its own risks, but it has one enormous advantage. When policy and engineering are aligned, timelines compress. And in breakthrough technologies, the first mover often becomes a default setter for standards, supply chains, and talent gravity. Now stack these perspectives together, and a single insight pops. Fusion isn't just an energy technology. It's a governance technology. Whoever figures out how to regulate it proportionally, serious about safety, but not paralyzed by the wrong mental model, gets more than power plants. They get advanced manufacturing ecosystem, strategic electricity abundance for industry exportable technology packages geopolitical leverage in a decarbonizing world. And that takes us to the moment where the story stops being policy wonk and becomes thriller again. Because there's a reason regulators move slowly that has nothing to do with fusion itself and everything to do with incentives. Picture 2032. The first real fusion electricity is delivered somewhere on Earth. The only question is, what had to happen for it to be allowed? There are 3 plausible paths, and each one rewrites the global energy map differently. Scenario 1, regulatory reform wins. The clean version. Governments create fusion-specific, risk-informed rules that treat fusion like what it is, Industrial radiological technology with serious oversight, but not fission-style catastrophe planning. Licensing becomes predictable enough that investors can underwrite it. Demonstration plants connect to grids. The first wave of commercial fusion shows up mid-2030s with strong public trust. In this scenario, the U.S. and allies keep leadership, not just in science, but in deployment. But it requires something rare. Sustained political attention on something that hasn't yet become a public crisis. Scenario 2. Workarounds become the product. The messy, very likely version. Fusion companies sidestep traditional pathways by building non-grid demo systems first, selling directly to single customers, data centers, industrial sites, deploying in special economic zones, ports, or tightly controlled campuses, choosing jurisdictions with clearer permitting, even if smaller markets. Fusion arrives, but unevenly. Island of abundance rather than a universal grid revolution. The first buyers are the ones who can afford premium power and want energy security more than cheap kilowatt hours. This is how a ban looks in real life. Not a law, but a deeder that changes who benefits first. Scenario 3. The stall and the brain drain. The tragic version. Rules stay ambiguous. Timelines slip. Capital gets impatient. Companies consolidate or collapse. Talent migrates to countries where building is simpler. And eventually, fusion succeeds somewhere else. Then Western governments do what governments often do. They regulate the successful thing after it already exists, importing technology they once invented. Now here's the twist inside these scenarios. Regulators aren't usually malicious. Their incentives are asymmetric. If they approve something new and something goes wrong, they own the blame. If they delay and nothing happens, no one gets fired. So the system naturally prefers later, which sets up the emotional climax. Fusion might be the safest nuclear technology ever conceived, and still be treated like the most dangerous, because the rulebook was written for a different era. And that leads to the question that changes the whole story. Is fusion being delayed for safety, or because the system doesn't know how to say yes without risking its own reputation? Here's the twist that makes the "they got banned" headline feel true even when no law says it. Fusion is colliding with a system that is rationally designed to fear success. A regulator's job is to prevent disaster. That's a noble mission, but it creates an incentive shape that's almost impossible to escape. If you approve something unprecedented and it fails, you're the person who let it happen. If you slow walk it, and the future arrives later than it should, there's no press conference titled, "We delayed abundance." So the safest career move is often the worst societal move. And fusion is the perfect stress test of that dilemma, because its upside is civilization scale. Fusion isn't a better power plant. It's a potential reset button on. Energy scarcity, industrial emissions, water desalination costs, synthetic fuels, like green hydrogen, geopolitical dependence on oil and gas choke points. There are famous analogies about fusion fuel abundance, like deuterium in seawater, but the real point isn't the poetry. It's the implication. If energy becomes cheap and clean enough, entire categories of trade-offs change. So now ask the uncomfortable question. If fusion threatens legacy economics, fossil fuels, yes, but also portions of the existing power market structure, who benefits from careful, indefinite caution? Because delays always create a winner. Sometimes it's nobody in the room. Sometimes it's the incumbents who can afford to wait. Sometimes it's the country willing to move faster. And the irony is savage. The U.S. proved ignition in a national lab tied to national security. Then the civilian commercialization effort runs into a licensing maze. Meanwhile, geopolitical competitors can frame fusion as strategic infrastructure and simply build. So BAM becomes a feeling. You can have the breakthrough, the investors, the talent, the prototypes, yet still be blocked from the one thing that matters, turning it on. Now, to land this story honestly, we have to resolve the tension with a grounded reflection. Fusion does need regulation. Tritium is real. Neutron activation is real. Worker safety is real. But there's a difference between regulation and paralysis. So the final segment answers a question that viewers will carry after the video ends. What would a sane fusion rulebook actually look like? One that protects people and doesn't hand the future to whoever moves fastest. If you strip away the hype and the fear, fusion regulation has a simple goal. Treat fusion like what it is, not like what we're used to. A sane fusion framework would start with a risk map instead of a legacy category label. It would ask, what radioactive materials are present, like tritium, in what quantities and how are they contained? What are credible acts and scenarios, and what are their realistic consequences? What worker exposures are possible during normal operation and maintenance? What activation products are created, and how long do they remain hazardous? What security and safeguards are needed, given that fusion doesn't use fossil fuel in a fission sense, but still lives near sensitive technology? From that, you build rules that are tight where they must be and light where they can be. Tritium control that's strict and modern. Accounting, leak detection, containment, emergency procedures, environmental monitoring. No shortcuts. Material and waste standards based on decay times. Activation waste managed responsibly, but categorized based on realistic radiological hazard and duration. Decades versus millennium matters. Performance-based licensing for novel designs. Instead of forcing every design into one template, regulators focus on measurable outcomes. Shielding requirements, release limits, operational monitoring, shutdown behavior. A fast demonstration pathway. A tiered system that allows prototypes and pilot plants to operate under control constraints. So learning happens in reality, not just paperwork. Predictable timelines. This is the underrated part. Even strict rules can be workable if timelines are transparent enough for engineering and finance a plan. Because the real killer isn't safety requirements. It's ambiguity. Now zoom out. If we get this right, fusion doesn't replace solar and wind. It complements them. Clean variable generation plus clean firm power, with less need for gas backup. And if we get it wrong, fusion still arrives, just not where you expected. That's the final paradox. Fusion may be the first energy source that's scientifically harder than it is politically, because the last barrier isn't temperature, it's governance. So here's the comment question I want you to wrestle with. If you were writing the rule book, what would you regulate hardest? Radiation risk, corporate accountability, or the speed of deployment? Because whichever answer you choose changes who gets fusion first. Next video tease. We're going deeper into money and geopolitics. Fusion space race. Why China, the U.S., and big tech are fighting for the first power plant. When energy changes, everything changes, and you've just seen why.